In this video, we'll discuss a theorem that is very similar to Thevenin's called the Norton's theorem. Norton's theorem also pertains to a two-terminal device or two-terminal circuit, and according to the theorem, it can be converted into a current source that is in parallel with a resistance. So if we have an actual circuit, for example, and we decide uh, that this part here is converted into a Norton's equivalent, that part becomes this one. Okay, so the converted part of the circuit is called a Norton's equivalent, and the challenge here is to find what is the current I sub n and the resistance R sub n. Similar to Thevenin's, in order to find I sub n, we also remove the circuit that will not be converted to Norton's equivalent. So we remove that part that is not to be converted. And then we apply a short circuit. That means we install a wire between the open terminals A and B, like that. Because of the short circuit, a current will appear between A and B. So we're interested on the current flowing from terminal A to terminal B. That current is the Norton's current I sub n. Okay, R sub n can be found in the same way how we determine the Thevenin's resistance R sub th. So we can use the two cases that we have shown before to determine R sub n. So let's have our first example to show how Norton's theorem works. So here in this example, this is the same example that we did for superposition and Thevenin's. So let's see if we'll get the same result. So again, we're asked to find current I sub naught. So let's find I sub n and R sub n. So we remove the 12 ohms and replace that by a short between the open terminals A and B, and determine the current that is flowing from terminal A to B. Okay, this current. That current becomes our current I sub n. Now, how do we find this current from this circuit, the current I sub SC? Notice that when we remove the 12 ohms and place a short, this entire um, area here becomes a single node. So let me apply a nodal analysis to determine our current I sub SC. Okay, so let me make this my uh, ground node, and then let me draw the branch currents. So let's say this is here, it's I sub 1. Okay, so this is I sub 2, and here is I sub 3. So the corresponding polarity are the following. So here it is plus, this is minus, plus, minus, plus, minus. So the currents, the directions are arbitrary. Then we apply. So this let's label this as our node v sub 1. Okay, so there are no more nodes that we can label. Uh, well, this one is 12 volts, and here this is 0 volts because this is also part of the ground node. This is also 0 volts here. Okay, so let's apply uh, KCL on this node here. So the KCL there would be current entering is I sub 1 plus, so 2 amperes is also entering this node here. So take note, 2 amperes is entering on this node, then minus the current leaving. So I sub 2 is leaving that node. I sub 3 is also leaving that node. We simplify the equation, and that will give us this expression. We then replace the branch currents in terms of the node voltages. So I sub 1 is, so this is I sub 1, so it's 12 minus V sub 1 divided by 6. Uh, I sub 2 is V sub 1 minus 0 divided by 3. And I sub 3 is V sub 1 minus 0 divided by 5. That will give us this expression. Simplifying, we can multiply both sides by, let's say, 30. Okay, that should give us this equation. And from here, we can solve the node voltage V sub 1. And that should give us this answer. Now, how do we compute for the current I sub SC? Now, we can utilize this node here and apply KCL there. So although this is just one node, uh, here, this is just one node, we can still apply a KCL here. So that means I sub 3, current entering that node, minus current leaving. So here, the 2 amperes is leaving that node, and then minus I sub SC, which is also current leaving from that node, equals 0. And from this, we can compute I sub SC. Um, we know I sub 3 to be uh, this one. Okay, so we can then compute for the current I sub SC, which will give us this answer, and that becomes our current I sub n. Now for R sub n, as I've said, this is equal to R sub th, and we have that before, which is 7 ohms. So after getting I sub n and R sub n, we can now replace the circuit that we want to convert to Norton's equivalent. So we attach the circuit to the 12 ohms, and let's proceed to compute for I sub naught. Now this circuit, as you will notice, is ripe for a current division because we have two resistances in parallel, and current is entering that parallel combination. So therefore, I sub naught is the current that is entering the parallel combination times a factor So that will give us this answer, which is the same as the previous answers that we have. Okay, let's have a second example. And here, this is the same problem that we have in Thevenin's. So we're asked to again find I sub naught, that is the current flowing through the 4 ohms. So what we did before was to convert this part into an equivalent circuit. So if we convert this into Norton's equivalent, that should give us a simplified circuit that would look like this, where the terminals A and B are these terminals. So this is your A, and here's your B here. To find I sub n, we remove that part of the circuit that will not be converted from the original circuit and apply a short at the open terminals AB. To find I sub SC, we can use mesh analysis. So let's say this is my, let me use a different color. So let's say this is my I sub 1. So I'm using a counterclockwise direction for my loop currents. So let's say this is I sub 2. And here is I sub 3. So I'm using a counterclockwise direction so that it will be the same direction as the given currents. Now, so I can take note the mesh current here in this loop here is not anymore 0 because we now have a short circuit, unlike what we have before in Thevenin's where it is an open circuit. So we can write KVL equation here because there's no current source. So let's proceed to do that. Let's use the shortcut in writing the mesh KVL equation. So this is the equation in this loop. So so our direction in in writing the equation is we're going uh, clockwise. So as we move around, we add all the resistances. So 3 plus 2 plus 5, we have 10 times the loop current I sub 1 minus the drop due to the loop currents outside the loop. So that is 3 I sub 2 minus 5 times I sub 3. And that we equate to 0. We know I sub 2 to be equals to, so this one should be equals to 4, and this one should be equals to 2. So we replace I sub 2 and I sub 3 with their actual values, and then we can find I sub 1. Now I sub SC in terms of the loop current should be equals to I sub 1 because that's the only loop currents or loop current that flows through this branch. So therefore, we have ISC, which is also our I sub n, equals to this value. R sub n is the resistance looking at the open terminals AB. So that should be the same as RTH. So we previously computed that in our example for Thevenin's, and that is equals to 10 ohms. So we put the values together, I sub n and R sub n, into our modified circuit. So now we have here R sub n and I sub n. So how do we solve I sub naught from the simplified circuit? So again, we can use a mesh. Let's assume uh, mesh currents here. So let me use a clockwise direction this time. So again, let me use I sub 1 here, I sub 2 here, and I sub 3. Okay. So take note, I sub 1 here, I sub 2, and I sub 3 are not the same I sub 1s that we use uh, in this circuit, because we're now dealing with a different circuit. Okay, so we can immediately determine I sub 3, and that should be equals to the opposite of 2.2. So this is our I sub 3 from loop 3. From loop 1, we can form the equation, KVL equation. So this is the KVL equation. So minus 12 plus 4 plus 10, that will be 14 times the current I sub 1, loop current I sub 1, minus any voltage drop due to the loop currents outside this loop. So that would be 10 times the loop current I sub 2 equals to 0. So let's call that our equation 1. Now we need one more equation, and that will come from this loop. So performing a KVL equation in this loop. So that would be 10 plus 10, that is 20 times the loop current I sub 2 minus all voltage drops due to the loop currents outside loop number 2. So that would be 10 I sub 1. So the drop here due to I sub 1 minus 10 I sub 3. So the drop here due to I sub 3 equals to 0. Simplifying, we already know the current I sub 3. We'll get this second equation. Combining the two equations, we'll then get I sub 1 equals to 1/9 ampere, which is also our I sub naught, because the current through the 4 ohms in terms of the loop current is just I sub 1. So therefore, our I sub naught is the same as I sub 1. You can also compute for I sub 2.